to start with a little story of my own life actually. This was back in 1983 when I had absolutely no idea what NMR was. I completed my MSc and I joined the group of Professor Atar Rahman. At that time, to be very precise, was September 13, 1983. And in that particular group, there used to be many very senior, very strong students at that time. These very nasty seniors used to ask the junior to present lectures. Whenever Professor Atarman wanted to start a lecture series, they always wanted to start from the most junior one. Because by the time the junior finished, Professor Atarman was either in UK or forget what was actually happening. And I was the most junior one at that time. A strong, big man caught me in the middle of the corridor and he said, "Who are you?" I said, "My name is Iqbal and I recently joined Professor Atarman's group." He said, "Okay, you have to present a lecture next week. We are starting a lecture series." And he gave me a topic which, with the handwriting of Professor Atarman, and fortunately I have all these notes with me. The topic says that you have to present a lecture on inadequate, incredible natural abundance double quantum transfer experiment. It was even so difficult for me to pronounce at that time. You see, there was a time when inadequate was developing. And I remember reading an article of Gunther about this technique. Very primitive, almost embryonic stage of the development of inadequate. And here I was, after 1 week, presenting a lecture on inadequate in front of Professor Tarman and in front of so many other people. I don't know how that lecture went, but I remember Professor Tarman calling me in his office and said, "You want to write a book with me?" And that was the biggest surprise of my life actually. After 1 week of joining Professor Tarman, I was hired to write a book as a co-author with Professor Tarman. I think this was because of NMR spectroscopy. A little understanding which I was able to develop because of the forceful interaction of a senior. And therefore sometimes the interventions of seniors are very important. Juniors must remember it. This all started from there. And I still remember we used to have a small 60 megahertz varying machine at that time. And in 1983 we acquired the first 100 megahertz Brooker machine, 90 megahertz Brooker machine. So in front of people who are actually working in the frontiers of NMR spectroscopy, my tale would largely be the tale of a person who is using NMR as a tool in the field of natural product chemistry. But realizing that we would have a lot of very young people who are equally excited about NMR, I thought I should really talk about some of the basics. Although this is an entire course which I would, inshallah, deliver very soon, perhaps a course of some 2 weeks or 3 weeks. But some of the slides would actually tell you the best basics of NMR spectroscopy. A lot has already been covered yesterday when Ellen and Dr. Asman talk about the developments both in terms of hardware, in terms of software, in terms of basic philosophy of inverse spectroscopy or pulse gradient field spectroscopy. I will not really go into that actually. I would rather start from the basics and giving you a little bit story of NMR, how it actually developed. I will start from a very important saying, a quotation from James Baldwin from Dyson Perrin Laboratory, Oxford. He said, NMR spectroscopy is perhaps the greatest, most important development which has the strongest impact on chemical research after the development of accurate balance. And it is so true actually, because I feel NMR is one discipline which has changed the whole scenario of field of chemical sciences, biochemical sciences, and so many other sciences. So that actually reflects the importance of NMR spectroscopy. And as we all understand what spectroscopy is, NMR is not different from other spectroscopy. It is a basic interaction of molecular architect, molecular structure with absorption of light, interaction with the light, absorption, emission, and scattering of light. The interaction between molecule and light and the resulting emission, absorption, scattering, and measurement, accurate measurement of these three phenomena would tell you a lot indirectly about the structure. And therefore, NMR is not different from the basic trivial UV spectroscopy, IR spectroscopy, Raman spectroscopy, in a whole range of different spectroscopy technique. NMR is not very different. The reason why I wanted to present this slide, because NMR generally scare people. The basic fact is that people think NMR is different from others. NMR is not different. NMR is very simple, at least at a conceptual level. And this is what I would like to present here also. This is our electromagnetic radiation. And there are a variety of different types of electromagnetic radiation depending on their frequency and energy. And each has a capacity to do something with the molecule. It could be X-rays or cosmic rays, which can break the architect of the molecule. Or it can be very benign gamma rays, radio waves and microwaves. It doesn't really harm your molecule, but carry out certain changes. For instance, in case of NMR, it's basically the nuclear spin which is affected. In case of UV, you're talking about electronic transitions. In case of IR, you're talking about stretchings of bondings and a whole range of different bonding changes, bond lengths, bond angles. So the electromagnetic radiation, depending on their energy, can cause different types of interaction in the molecule. NMR is the most friendly one because it doesn't really harm your molecule at all. It just changes the nuclear spin, the orientation of nuclear spin. And without going into details of a variety of different types of spectroscopic technique, ultraviolet, as you know, affect at the electronic level, infrared is the vibrational rotation level, and a variety of different types of information which you get. NMR, when nuclei placed under the static magnetic field, their spins are changed. And this gives you information about the electronic environment of nuclei, their numbers and numbers of neighboring atoms. See, yesterday Alan was talking about the content of information which you get from different spectroscopic techniques. NMR is perhaps after X-ray, which is not a spectroscopic technique per se, is a different concept. But among the normal spectroscopic techniques, the information content of NMR is the maximum one. You get the maximum information out of NMR experiment as compared to other information, because this gives you a whole picture of the electronics of a molecule. And electronics, as we all understand, the basic architect of a molecule is basically the electronic environment, which tells you about the types of atoms, numbers, and connectivities. So, comparison among the different spectroscopic techniques, take C13 and proton NMR as a different domain of NMR spectroscopy. The information content is very good actually. The information content is very good. Identification for whole very expensive and whole range of different problems associated with mass. NMR is not free of problems also, but the information content which you get from NMR spectroscopy complement and is much larger as compared to other techniques. No other technique is more descriptive in terms of name, nomenclature than NMR spectroscopy. The name tells you everything. NMR, study of the nuclear spin, magnetic, under the influence of applied magnetic field, resonance, when a nuclear spin placed under the influence of magnetic field, it resonates in the presence of radio frequency, and you record the whole thing. So if you understand the name, you understand the technique. 50% of understanding of NMR spectroscopy is just understanding the name, and this is perhaps the most sounding acronym of any technique. It tells you a lot about the technique itself. This was the first NMR spectrum, 1951, Oxford, Stanford, ethanol. And again, if I repeat, which I presented earlier, this was an exciting time for chemists. For physicists, I was very happy. Physicists, the people who always develop a spectroscopic technique, they're the first who develop a spectroscopic techniques, and then generally somewhere in between disappoint and start doing something else. Chemists take it up. Chemists, after seeing this spectroscopic, this spectrum, were very excited because they could understand that ethanol in fact has, based on the nature, in fact has 3 different types of hydrogens, protons. And you see 3 different peaks. Physicists were disappointed. Physicists were looking for a technique. Physicists were looking for a technique which gives them a quantitative measurements of all the protons or NMR active nuclei present in the molecule. For them, it was an unwelcome complication. They didn't really like it. But this potential really tells you a lot about the development which eventually took place in future. So if you look into the chronology of development, it started from paraffin and water, but 1951 when the chemical shift and spin coupling, based on that ethanol spectrum, people start understanding the chemical shift and spin coupling. In 1960s, a very important development of signal averaging for improving sensitivity. When people start talking about signal to noise ratio, people start using techniques in which different spectrum were used to be recorded, and based on the simple fact that noise are random and signals are overlapping, one can enhance the signal to noise ratio. And then the advent of mathematical procedure of pulse Fourier transmission technique, which has actually changed the whole face of NMR spectroscopy, because people have realized that they don't really need to record frequency domain, spectrum and frequency domain. They can go for a time relaxation measurement, and then by using this mathematical procedure, convert these time domain signal into frequency domain signals. 1970s, when people start developing superconducting magnet, Alan yesterday summarized very interesting developments in terms of superconducting magnets. This was a time when people start talking about high resolution, large NMR spectrometers, which can go out of domain of a permanent magnet of iron magnet. So people start talking about superconducting magnet. And let me tell you what superconducting magnet is. These are very, very sophisticated, very interesting alloys of some very rare metals like niobium or different types of metals. And when you place them to an absolute helium temperature, liquid helium temperature, which is minus 270 Kelvin, and you charge them with electricity, you discontinue charging, and they become a superconducting magnet, because at that particular temperature the resistance is minimal, and therefore they allow you to go a very high field measurement at a very low cost, because no other permanent magnet can allow you to go to that level. So this was an important development. In 1980s, development of multipulse and two-dimensional NMR spectroscopy, and I'm probably show you one or two pulse sequences. NMR has its own language. Now people talk about not irradiating the molecule at once, but they are talking about multiple of pulse sequences, a whole cascade of pulses which bring, in a very predictable way. NMR is very predictable now, because when you have a nuclear spin, you know precisely what type of pulse shape, strength and duration would bring this nuclear spin to what state. So it's a very predictable domain, in which you can predict your nuclear spin at a different level by using a cascade of pulse sequences. And then in 1980s also, when Genus first presented the idea of COSY, so-called two-dimensional NMR spectroscopy, and in a conference, the two-dimensional NMR spectroscopy become almost practically possible after 10 years. He presented in 1971 precisely. In 1990, routine application of pulse field gradient. But let me talk about two-dimensional NMR spectroscopy. You see, in a very layman language, if you have a very complicated NMR spectrum of a molecule like brevetoxin, you literally have absolutely no idea what you can see, because in proton you have an inherent problem of seeing everything in a scale of 0 to 10 or perhaps 12. And in this very small scale, if you have 200 different atoms, 200 or 300 different hydrogens, you see literally nothing out of it. If you can somehow add another dimension and you start looking from the other side, then you would be able to get more information out of the whole experiment. So remember, everything which is possible by 2D NMR spectroscopy, which you get out of 2D NMR spectroscopy, is possible to be obtained from 1D NMR spectroscopy. The only difficulty is that interpretation is very difficult. So this was mainly started with the help for the help in interpretation. So 1990, this pulse field gradient started. Yesterday it was very nicely presented. And signal selection development of coupled analytical methods. This has also been demonstrated yesterday. This breakthrough development of coupling a chromatographic instrument with NMR spectrometer was a turning point in the usefulness of NMR spectroscopy. The beauty of this technique is, as you understand, chromatography is a very, very different types of technique. NMR spectroscopy is a very, very different type of technique. And it literally took people, the dream was always there, back in 1970s, people were talking about coupled techniques. When people developed GCMS, LCMS was even, the concept of having LCMS was even earlier developed than GCMS. But there was an interface using this chromatographic technique, which is extremely rapid, which generates a tremendous volume of solvent, and using NMR spectroscopy, which is inherently slow, which takes time. The so-called coupling of, so-called marriage of two different domains, two different personalities was the most difficult one, because the interface which need to be developed required a lot of science. And still I feel that it has not to a level. It is still LC and NMR, and there are some intervention which you really put something by using the real LC NMR is yet to be developed. Maybe in 10 years time people would have LC NMR, but so far it's mainly LC and NMR and something in between. So this was a development which still requires a lot of further progress. 2000 onward, use of high sensitivity superconducting probes. Yesterday people talk about cryo probes of different nature. People talk about different types of and sizes of NMR probe. And 2000 onward, you were really looking for flow injection NMR, which would be literally a real LC NMR. You would really be looking for the demise and death of NMR tubeless NMR. You're looking for a benchtop NMR. I don't know when these dreams will realize, but these are actually going on. Now, let me tell you something very interesting. Started by physicists, taken by chemists, now in next 10 years time, NMR will be largely used by biologists. Most of the most recent developments are in the field of biological applications of NMR spectroscopy. Why bother learning NMR? You see, you have two ways of doing it actually. You can hire a good person, a chemist who understands NMR spectroscopy, who can interpret result for you, and you just submit your sample to Surface. Surface run these NMR and give it to somebody else, like most of the companies are doing it. You see, you go to Abbott, you go to Eli Lilly, you go to Bristol Myers, you go to large companies, they have absolutely no idea what NMR is. They synthesize compound, they isolate compound, they give it to NMR section, and there are whole teams of sometimes 100 people doing interpretation for them and doing the structure elucidation for them. But being NMR, being a natural product chemist, when everything is already automized, when you have a plant extract, you carry out HPLC and you isolate a compound and you give it to somebody else for structural elucidation. What is your use? Absolutely no use, no excitement, no science in it actually. So the whole domain, so first thing is for the basic thrill and excitement of knowing a structure of an unknown compound is a basic driving force of learning NMR spectroscopy. Without understanding at least the basic concepts of NMR spectroscopy, is very, very difficult to effectively utilize the recent development. First thing, the thrill and excitement of knowing the structure, but it offers a lot. The structural sedation, synthetic organic chemistry, an analytical tool for synthetic chemists, for natural product chemists. If you are a physical chemist, and if you are actually working in the field of understanding the dynamics, or even if you are a biochemist who are trying to understand the interaction of a small molecule with a very large molecule, like an inhibitor with an enzyme, these are all dynamic processes. They are changing with time. And therefore, reaction kinetics, the study of equilibrium, the interaction between ligand and substrate, a whole range of different paradigms. And this all can be learned from NMR spectroscopy. Being trained as a structural organic chemist who try to understand and appreciate different types of spectroscopy and crystallographic technique, I still feel the X-ray crystallography has a lot of limitations, although it gives you a complete picture of the molecule. But unless people develop a solution X-ray crystallography, NMR would still be the stronger technique and better technique than X-ray crystallography. Structure, the informations, you get a three-dimensional structure of proteins, DNA, complexes, polysaccharide. In drug designing, the structure-activity relationship by NMR spectroscopy, so-called SAR by NMR. This is a very interesting technique. SAR by NMR, SAR by NMR. You know, in Abbott, you will find a lot of people talking about structure. It was all started in Abbott, Chicago. The structure-activity relationship by using NMR spectroscopy. I don't claim to be understanding the whole concept, but what I understand is something very interesting. You see, you have a large molecule like an enzyme, alpha-glucosidase or acetylcholinesterase or whatever. This very large molecule, biomolecule, that enzyme requires certain prerequisites, structural features in the inhibitor. For instance, your inhibitor should interact with the active site or peripheral site, whatever. And in order to have this interaction, it should have certain structural feature. For instance, if your enzyme has minus charge, your inhibitor should have a positive charge somewhere. If your enzyme has, for instance, a carboxylate or something like this, you should have, you know, the whole paradigm of molecular recognition interaction, whether van der Waals interaction, whether zootropic interaction, whether charge, species, whether general affinity, hydrophobic, hydrophilic interaction, there need to be structural complementarity, so-called key and lock model. Your key should have compatibility with the lock. Now, in order to discover the structural features which requires to be built into the inhibitor, in order to have its maximum interaction with the larger molecule enzyme, there are a lot of very innovative ideas were developed. And SAR by NMR was perhaps the most revolutionary one. Although I know nothing has developed from that technique so far, but that promises a lot. Now what you need to do, you take your large molecule, you take smaller molecules of different functionalities, literally only one functionality. For instance, you take small, let's say ammonium salt, you take a small carboxylic group, not functional groups as well. You can't have a functional group alone. They're small molecules with different functional groups, small little molecules. And you mix these smaller molecules with larger protein or that enzyme. And then you start understanding the interaction. You see, there are a variety of different ways in NMR spectroscopy in which you can see the interaction by negative NOE, by Rosie, a whole range of different changes which you see in the molecule, in the structure of a large molecule, conformation and configuration changes. Now, if you observe that out of these very small molecules, several which you have added into your enzyme, some of them are interacting. For instance, out of 10 different small molecules, functionality, ketone, acids, positive charge, aromatic, a whole range of different things, you find that your amide is interacting, amino charge is interacting. If you find that one of the aromatic ring compound which you have added with the aromatic ring is also interacting with the enzyme structure, that provides you a very important information. This information provides you that now you have to develop a molecule which contain all these functionalities in the right direction, in the right distance. So these small molecules which are interacting with the enzyme, or not doing anything with the enzyme, because for enzyme inhibition you need to have a whole structure which fits very nicely in the active site. But these smaller little molecules then need to be built in by synthetic chemistry into a molecule which is compatible with the structure, with the active site of the enzyme. So this was an exciting development, and now more than ever, NMR is now used for medical diagnosis. I was fortunate to visit Besenberg, Karlsruhe, and different Brucker establishment. Amazed to see that most of the developments are actually going in wide bore probe, in which you can put human being into an NMR machine already, MRI. But now they're developing wide bore probes in which you can put your rats and your rabbits, I don't know how, insects or whatever, and then so-called biopsy analysis, so-called metabolite analysis, so-called tissues and biopsies, a whole range of different development which is currently going on in the field of the biological application of NMR spectroscopy. So this is the future. Now, NMR and natural product chemistry. Why NMR is important for natural product chemistry? Natural product chemists are still the largest user group of NMR spectroscopy, and I claim this still now. Most of the NMR machines are actually sold to people working in the field of natural product or natural product related sciences. Natural products are generally small in quantities, very small in quantities, sometimes bulk supply. You work on a rare sample of a plant, you isolate few milligrams, perhaps 1 or 2 milligrams, and that's it. Nobody will ever isolate that compound. Nobody has ever isolated that compound earlier. So generally small in quantity, so you need to have a technique which is very sensitive. Unfortunately, NMR is not, and therefore you need to develop a lot of NMR tools. Natural products are novel in structure. In synthetic chemistry, you always know the structure. You know the structure, you put certain reagent, you know what type of changes will eventually occur. 90-95% time, the predictions are true, and you see reduction of a carbonyl group or oxidation of a carbonyl group or breaking of a bond or reduction of a bond. Predictable. NMR, natural product chemists, they have absolutely no idea what they're dealing with unless they develop some interaction and they're working on particular types of chemotaxonomic group of plants. They're novel in structure. Generally, natural products possess chirality. They are globular. Synthetic chemists are flat. Synthetic molecules are generally flat. If you look into the synthetic, except in cases where people have synthesized a natural product, generally the small racemic asymmetric organic synthesis generate flat molecule. Right? So if you look into the overall development of new chemicals, so-called pharmacophore or so-called small molecules, these are small flat molecules. Natural products are globular. They have a third dimension. invariably. You isolate a tritropine, you isolate indole alkaloid, you isolate ramidoxin, you isolate a whole range of different compounds. They are globular and they have a third dimension. And since they have a third dimension, you need to have a stereochemical interaction. When you have a third dimension, you need to know the stereochemistry. So they possess chirality. The reason why they are able to interact, why natural products are able to interact with biological system, because biological system is also globular. Biological system also has a third dimension. There is no single biological molecule in the body which is flat. Even a small little amino acid has a third dimension, right? Except in organic salt, all the biochemistry of a living system is globular. It has a third dimension. So since it has a third dimension, your natural product is compatible with that. Your natural product has more possibility of interacting with the biological system than a small racemic molecule which is synthesized by synthetic chemistry. So they possess a globularity, they possess chirality, and they have a changing conformation. For that, and they have an interaction, and by virtue of by virtue of these features, they have capacity to interact with a large biomolecule. Now, tell me one technique which can provide you confirmation analysis. Very few. X-ray is a solid state confirmation. You freeze your molecule. You have everything frozen in time. It doesn't really give you how a molecule is going to behave in a solution conformation. So NMR is one technique which actually more compatible with the globularity and with the chirality of a molecule in 3 dimensions and how it behaves in solution. So-called dynamic changes which are actually occurring in the molecule can only be seen by using NMR spectroscopy. Then the so-called development of hyphenated technique. No other group in the world have benefited more with the development of hyphenated technique than natural product chemists. You take a chromatographic method, you isolate compound, you take it to NMR, mass, IR, ICP, the whole range of different molecules. And now there are range of online surveys available by which you can see whether your compound which you are isolating is novel, new, known, or whatever. And a part of it goes into 96-well plate, and you get the biological screening also. So in one go, online survey by using chromatographic method, NMR, and only yesterday I was reading that even the proton NMR spectrums are actually available for probability matching by ACD. It was only C13 prediction software, but now 34,000 proton NMR spectrum is available by ACD, by which you can compare the NMR of a compound coming out of chromatographic machine like LC, and you know precisely the structure whether it's known, so-called de-replication, and then you take the biological activity also. So the development of LC NMR was a major breakthrough in the field of natural product structural elucidation. These are the machines which are actually used. We have ordered 600 ultra shielded with LC systems, so we would soon have this facility available. Now, in next 15-20 minutes, there's a terrible slide, and I don't think you'll be able to read it, but let me read it for you. To be an effective user of spectroscopic techniques, you need to develop a sense and understanding of a real chemist. I remember Professor Salim Siddiqui used to say that the structural elucidation, elucidation starts when you touch a plant. And it's such a beautiful saying, you know. You go to a plant and you are intending to work on that particular plant. Right at your touch, you test and spin, you start understanding these structures. We all understand that the aroma which is coming out of plant is because of small terpenes, right? We all understand that bitter tasting plants generally contain alkaloids. We all understand that when you take a leaf and rub it like this, break it and rub it, and if you see some foam coming out, it's because of saponins. Yes, when you take a plant, you rub it on your fingers and you find that you have some kind of irritations or some kind of binding. It's because of lignins and all that. So structural sedation requires a holistic approach of understanding the nature per se. Preparation of sample is very important. You always start with a pure sample, although my friend would eventually talk about DOSI also. But NMR spectroscopy or any spectroscopic technique is still dependent on the purity of sample. I'll just pass on. Maybe next time, next. Yeah, next. Now, what are the typical protocol? As a natural chemist, how you want to start with? Remember, NMR is a non-destructive technique. So, to all practical purposes, if you are a careful chemist, you would not really lose your sample, unless your solvent is nasty and it does some chemistry with your molecule. NMR is safe and sound, and you recover 100% of your sample without any loss if you are careful. You go for one-dimensional proton NMR spectrum. It provides you information about the chemical shift, coupling constant, integrals. Chemical shift is the environment of protons, environment where they are actually located, whether they are methyl, methoxy or N-methyl, whether they are just quaternary methyls, whether they are aldehydic proton or a carboxylic proton and a phenolic proton, environment. Coupling constant tells you about the neighborhood, which neighbor is doing what effect on your particular nuclei. Integrals tells you the number of protons present. So it provides you a lot of very important information. To all practical purposes, if you have a small molecule, your interaction with the NMR spectroscopy is finished at this stage. You don't really need to go through all this. And this is again, I would really like to emphasize that not sometimes, but most of the time, we have a tendency of overdoing it. Even if we know the structure, we still go for HMBC, toxi, and I don't know what not. You have to just remember that if you know the structure, and if you have a simple molecule, you just have to rely on the data information which you receive from 1D NMR spectroscopy. But if you really need to know more about the structure, then you go for COSY first. Proton-proton interaction. Which proton is interacting with which proton? Correlated spectroscopy. Now, if you're not very satisfied, you go for C13 NMR spectroscopy. Remember, C13 NMR spectroscopy, even with the advent of inverse probe and whole range of, is still insensitive technique. Then you go for so-called inverse spectroscopic techniques, HMQC, interaction between proton and proton. So start from here. Information about proton alone. COSY interaction, information about a more clearly understood information about proton-proton interaction. C13 NMR spectroscopy, information about the carbons, the types of carbon present, sometimes the multiplicity. HMQC and HSQC, carbon-proton interaction. HMBC, long-range interaction. NOE, geometrical consideration, so-called dipolar coupling, you see the chemical analysis. Toxi, total correlation spectroscopy, in which you see the interaction of protons, all the protons present in one spin system. There are literally hundreds of NMR techniques, so-called software have been developed for structural elucidation. But these are perhaps the most important one. These are the ones which generally natural product chemists use. Although you have a range of different types of techniques available also. Now, what are the types of NMR spectroscopy? High resolution mode, homogeneous solution. High power mode, you go for relaxing nuclei, exhibit broad lines, so-called high resolution, magic angle spinning. The study of solid, you go for magic angle spinning techniques. 3D imaging, magnetic resonance imaging, resolution family. These are 4 broader categories of NMR spectroscopy available. And within them, there are a number of other. And what NMR can measure? Functional group analysis. So literally, you don't need to have IR. Now, I don't want to be a person who is so cynical about other techniques also. NMR structural sedation, as Dr. Asper said yesterday, is a technique. It is a process in which you need to have information from different complementary techniques. There is always good to reconfirm from one another technique. Functional group analysis, chemical shifts, bonding connectivity and orientation. The coupling provides you bonding connectivity and orientation through space coupling by using Overhauser effect, molecular confirmation, a whole range of different biological molecules, enzyme sequence and structure. So-called tertiary structures of proteins can be determined by NMR spectroscopy, and chemical dynamics when you are actually looking into the changes occurring in the molecule in the dimension of time. NMR machine, as we all understand, is fairly simple. You see, Bruker is developing a lot of these new tools, but it's just a magnet and a computer, a magnet which contains your radiofrequency synthesizer, your radiofrequency reader, and this is interfaced with a computing system which then carry out the rest of the manipulation. So it's a fairly simple machine. This is your magnet, and I was fortunate to see the earlier magnet in which you see a permanent magnet in which you place your sample in it. So this is your magnet. Detector and frequency generators are now all built in in a magnetic assembly, and you record. Here you can introduce computing power in order to manipulate from the data which you are generating out of this whole process. Bruker ultra-shielded machine, this we have in our institute, and it's all is related to this tiny little thing, so-called nuclear spin. This is your magnetic field. What you have done a very simple operation. You prepare the sample. It contains different nuclei. You place them into a very high power magnetic field. And what had actually happened, the only thing which actually happens is that nuclear spin align themselves along the magnetic field or against it. So-called principle of Boltzmann distribution axis. Here you have more spins orienting towards the magnetic field than against it. And this axis, the small axis, is so-called Boltzmann distribution axis. And this Boltzmann distribution axis is represented by a vector, so-called resulting vector, a bulk magnetization vector. This bulk magnetization vector, which is representing a tiny population of nuclear spin, which are in axis along the magnetic field. You play with this. The entire cascade or entire story, the so-called theory of NMR spectroscopy is based on this bulk magnetization vector. You play with it. You play with this bulk magnetization vector. You sometimes bring it here, 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 you sometimes bring it here. By what process? You cannot. Remember, these are magnetic vectors and they have certain polar axis. In order to bring them into XY plane, you need to have a radio frequency pulse. And that radio frequency pulse provides a torque, so-called nutation factor. torque which bring it to a y or x depending on the orientation of this pulse. Now, I want to tell you something very interesting. When the NMR spectroscopy started, it was a very conventional technique like IR. When you have electromagnetic radiation introduced into the system, and you see this transition occurring. NMR inherently insensitive. NMR, when you have radio frequency, depending on magnetic field or radio frequency, whatever you can vary, you sweep radio frequency pulse, and as soon as a certain nuclear spin absorb, you see an absorption line. So it was literally taking ages to develop one spectrum. Now, with the pulse NMR spectroscopy is a beautiful concept. Whoever developed it must be a very smart person. The concept is that you have all of your nuclear spin, you use a burst of radio frequency, a whole range of radio frequency, a very strong radio frequency, strong enough to excite all of them together. You give this radio frequency pulse to your sample, all the nuclear spin excite. When this nuclear spin excite, you get nothing out of it. The experiment starts after that, when they start relaxing. When they start relaxing and they want to achieve the thermal equilibrium which exists in a natural magnetic environment, this relaxation is then recorded as NMR signal, so-called FID. So depending on the radio frequency pulse, you can bring this vectorization vector to any place on XY plane. And when they are excited, they have to relax because they are in abnormal state of energy. They have to release the energy. There are various ways of releasing energy. You can go to one of our book in which Professor Tarman's first book on spin. That has a very good chapter on relaxation mechanism, a variety of different types of relaxation mechanism. But in a nutshell, bottom line, this relaxation is recorded. So NMR spectroscopy is not an absorption spectroscopy anymore. Remember, it's also not an emission spectroscopy anymore also, because you don't record the whole thing. The energy which you have provided doesn't really come out from the sample as a whole, because it just orient and disperse in a variety of different ways also. You record only a portion of energy which is involved in relaxation and is something different. And this relaxation, the energy which is coming out of the system is then recorded in a time domain, so-called frequency free induction decay. Next. This is the NMR spectrum. Who would like to see this NMR spectrum? It's probably, I don't know which sample is this, but maybe a sample which contains maybe 4, 5, 6, 7 different protons. Not a very complex sample. And these lines are actually representing the energy loss. When it 100% relaxed, which is never, because infinite time requires, you see a baseline. So this energy is released, and your detector record this energy which is coming out of this as a result of relaxation. This is a time domain signal. Remember, this is just a time, so-called relaxation time. Some nuclei take more time to relax, some nuclei take less time. The nuclei which takes less time are already relaxed at this point of time. The nuclei which take more time. So it's just a time axis here. Energy and time. So-called free induction decay, free of the influence of any radio frequency. Induction because it is inducing a current into amplifier coil of detector. Decay because it's decaying actually. It's just decaying and it's going back to the thermal equilibrium. This frequency, free induction decay is then converted into frequency domain, and for this you need a mathematical process which is called Fourier transformation. Now, remember, your computer cannot read lines. Computer can only read numbers. Computer is not capable of reading lines. Computer can read only the number. So you have to convert the whole thing into numbers. And when you convert the whole thing into numbers, so-called analog to digital conversion, then you carry out a mathematical process with these numbers, and you get from FID to a time domain signal. Next. Next. I don't know where. But your spectrum which you see, the so-called frequency domain spectrum. Now, the purpose of putting this slide here is just to tell you something very simple which has already been mentioned yesterday. NMR is a field which has its own language. Remember, musicians write their course and they use a language of music. The NMR software writers, people who are developing new sequences, use this language. This is the language of NMR spectroscopy. And a capable of NMR scientist would be able to read and translate the whole thing into an experiment. See, for instance, yesterday, this is a 90x pulse. This slide is a 90x pulse. What it actually means? It actually means that your bulk magnetization vector is rotated to a 90 degree by using a radio frequency pulse which was introduced from the axis, 90x pulse, right? This is 180x pulse, 180, it goes to the negative side, and these shapes are gradient shapes, a range of different types of pulses. The distance between 90 and 180 is the distance between two pulses. This is your free induction decay. This provides you information about decoupling because this is two nuclide experiment. And the whole range of different. So this is a very the language which is not very difficult. I mean, even a person who has no understanding of NMR per se in terms of development of NMR pulse sequence can translate some of it. So these are the pulse sequences. Remember, all the COSI, TOXI, HMBC, HMQC is in this form. So-called block presentations of vector presentation, block presentation of NMR experiments. And this is the vector presentation of NMR experiment. Remember, the bulk magnetization vector is from Z to XY plane, split it into static and mobile. You see two lines, a whole range of different experiments which. So you relax, you introduce a pulse, you acquire the signal, you carry out FID, and you can then see a frequency domain signal. Next. Now, out of the whole exercise, you get a lot of very useful information. For instance, yesterday depth was mentioned, polarization transfer. This is a natural product, and if you want to know how many carbons you have, there are a variety of different ways of doing it. You can go for high resolution mass spectrometry. HR, EI, HR, MS, FAB, high resolution mass will tell you how many carbons. But they are not going to tell you these carbons are of which type actually. So-called multiplicity, either they are metals. NMR provides you a very useful information. And first of all, NMR provides you information how many carbons. Simple peaks. How many peaks? You see more peaks? How many carbons? Their dispersion into this scale, chemical shift, provides you information about their environment, whether they are methoxy, they are N-methyl, they are quaternary carbon, they are CH2, whatever. The environment, and this polarization transfer experiment, which is a tool to get sensitivity enhancement also. With spectral editing, you get information about the multiplicity of signals also, which is a methyl, which one is CH2, which one is CH, which one, if you carry out editing, which one is quaternary carbon. So multiplicity information, and then the whole sequence, chronology of development and synthetic NMR spectroscopy in which people started from a normal C13 to broadband decoupling and a whole range of different things. But this polarization transfer experiment, one application in natural product chemistry is to get the multiplicity, the type, the number of different carbons which are present in your very complex molecule. Two-dimensional NMR spectroscopy, as I said, the difference between one-dimensional NMR spectroscopy and two-dimensional NMR spectroscopy is very simple in a layman language. Although one can translate into evolution time, one can translate into a whole range of different sequences. You see, if you want to know which proton is interacting with which proton, you have several options to use. The first option is double resonance experiment. For instance, if you are a chemist working in late 70s, you had only one option of using it. When I went to Pennsylvania State University and when I happened to be interacting with Lloyd Jackman, the man was using double resonance experiment, and he was a very large steroids. It's a very, very steroids. So he was assigning the chemical shift of every proton by using so-called spin decoupling, so-called double resonance experiment. For instance, if you have a molecule and you see this methyl next to CH2, you irradiate this methyl, bring it out of the domain of X-Y plane, bring it to the excited state. Now this CH2 is simplified because it doesn't have any interaction with methyl, right? So it proves that CH2 is next to a CH3, double resonance experiment. Literally, you can get information about the coupling of different protons in one dimension also. But in a molecule in which you have so many protons, for instance, triterpenes or steroids, when you have literally all CH2s coming in one region from 0.5 to 2, this large envelope of signals, double resonance never work. It doesn't really work. For that you need to go for a correlated spectroscopy. In certain cases it doesn't work also, but it just provides you a second dimension. For instance, if you have a lot of mountains, and if you're watching mountains from one dimension, and you have a series of mountains one after the other, you see all of them overlapping. But if you go to a second dimension, if you elevate yourself and you go on top of them, flying on a helicopter, you would start looking them into in the right perspective, because you would start differentiating between them, and you got a second dimension. So in my opinion, although I try to understand the whole cascade and the concept of two-dimensional NMR spectroscopy as a layman learner of NMR spectroscopy, this is just adding a dimension to interpret the results. Thanks. Again, NMR language. In two-dimensional NMR and one-dimensional NMR experiment, you see only one difference. The one difference is that in these different experiments, remember these are discrete different experiments. And in this experiment and in this experiment, the only difference is between the delay between two pulses. And remember, when you add a variable in experiment, you get a second dimension. The basic concept of adding dimension, when you add a variable into experiment, you get one dimension extra. This is what you get out of 2D NMR experiment. We have seen what we get out of one-dimensional NMR spectrum, interferogram. In two-dimensional NMR spectrum, you get something like this. And then you have to carry out mathematical process not once but twice. Two Fourier transformation. And two Fourier transformation, next, you get something like this. So this is time. Each line is representing a different experiment, but each line is different from the other because evolution time is different, two time domain. Then you carry out one mathematical operation and you convert T1 into frequency domain. You see distinction in terms of interferogram, and when you carry out one more Fourier transformation, you have frequency, and you see experiment like this. Now the only thing which you need to do is to plot it and start looking from the up, and you see all these peaks. These are so-called correlated spectroscopy. This is what your two-dimensional NMR experiment look like. It has two scales, one resulting from FID, the other resulting from the impact of evolution time on FID. This is the sequences which involve, this is a raw two-dimensional data of the NMR. The work of magnet, radio frequency oscillator, detector all finishes at this stage, and all this sequence is the work of a mathematical computing process. So it's all computing which convert this data into a two-dimensional NMR spectrum. These are different types of NMR, proton NMR, C13 NMR, and this is your two-dimensional NMR spectrum for a very small, simple molecule. You go on, please. This is hetero-J resolved. The hetero-J resolved in which you see hetero-J resolved in which you see the coupling constant in terms of carbon scale. Next. This is your correlative spectroscopy. This proton correlate with this proton correlate. So this is your diagonal line, and all off-diagonal peaks after symmetrization will tell you about the coupling between different types of protons. This is inadequate, so-called incredible natural double quantum transfer experiment, in which you see coupling between carbon and carbon. So the whole architect of organic molecule can be developed by using inadequate. The problem is that this inherently a very insensitive technique, because you are literally working on carbon 13 next to carbon 13, which has possibility of 0.001%. This is inadequate of a small molecule. Now, just for the sake of interpretation, which one is perhaps the most downfield signal? This one. This interacting with this, and this carbon is next to another CH2, and this CH2 is next to this petal. The whole framework of a smaller molecule can be seen in the whole inadequate experiment, but larger molecules can also be. This is for a relatively more complex molecule. Next. Next. For instance, this molecule which was isolated by Sharma, you see there are three discrete moieties in this molecule. Flavonoid, glycoside, you see this flavonoid, you see sugar A and sugar B. Now, although it's not a very complex molecule, but in this case, most of these protons in sugar are overlapping. This is fine because this different types of protons, and you can interpret them largely. But these two, and in cases, for instance, Dr. Bakar group is actually isolating saponies with several sugars. Now, the chemist has a very apparent option to hydrolyze them, and then identify these sugars also. But TOPSy provides you flexibility of recording proton NMR spectrum without hydrolyzing and chopping them up. Next. So for instance, in this case, you see the proton NMR spectrum of this sugar. Next. Again, the same slide. Of different types of, as many, depending on the spin system, you can record separate proton NMR spectrum of every spin system. Now, in my opinion, this is perhaps one of the most important development in NMR spectroscopy. The development of TOPSy has really changed the whole shape of interpretation of NMR spectroscopy. I will not really show much of these spectra because most of you are aware of it. The only purpose was just to tell you that NMR spectroscopy is and will remain be an important tool for natural product scientists, although it has now a lot of new dimensions, especially going into the biological investigation, going into biotechnology, so-called biochemistry, lithium science, surface sciences, a whole range of different applications. Thank you very much.